The next talk is by Ryan Elandt from Cornell University.
Hi, I'm here to talk about the controller for TikTok. This controller combines three main ideas: on-orbit matrix dynamics. It uses the affine linear relationship between accelerations and torques, as well as Geyer's reflex ideas. I'd just like to thank some people who helped me out, the Department of Defense, as well as Tuan Kulin's really awesome Julia rigid body dynamics library that he's going to talk about tomorrow. So TikTok is about the size and weight of an 8-year-old child. It's designed to be energy as efficient as possible using serial chain gear reductions, and this is a picture of what it looks like currently. I think Jason talked about it, the foot of it on Monday. So the structure of the equations of motion are relatively well known. The important things for the purposes of this talk is on the right side, the affine linear relationship that exists between accelerations as torques, as well as constraint forces and torques, where the large A and B are row matrices and they get dotted with a torque, and then there's a constant that depends on bias forces, whether that includes centrifugal terms. And these relationships are unique even in double stance, so we don't have to worry about weird configurations or uncontrollability or things of that nature. So many approaches use things like quadratic cost, state space dimension reduction, which includes inverted pendulum models, as well as trajectories and trajectory optimization. I want to take a different approach that just assumes that trajectories and control can simultaneously emerge from certain combinations of features. So what do I mean by features? I just mean intuitive 1-degree explanations of walking behavior that may include kinematics, as well as forces, things like compliance, stiffness, impedance, things like that, as well as kinematics would be swing foot clearance, arms moving in opposite directions, things of that nature. So this idea is not my own. It's at the very least it's Hartmut Geyer's, who approximately says that reflexes and behaviors cause walking. You can see the videos and read his papers, they're rather interesting. But the architecture he outlined has a couple of limitations that include each objective describes the torque of only one motor, as well as algebraic loops exist because he includes the current normal forces in to tune the stiffness parameters. And so which is not a huge issue because he's using soft contact, but if you want to extend it to hard contact, you'd have to figure out a way to do it. And I can avoid both these issues by using controllers that have the same affine linear form, a similar form to the inverted dynamics, and basically take a bunch of objectives, all written in this form, use them simultaneously, solve the system, and get a controller. So here's an example of this for a torque. In this case, we have joint 2. We want it to depend on normal force 3. We write out the equations in the typical way, and then just noting that although it may not obviously be an affine linear statement, each of the confusing terms is itself an affine linear statement. And if you do the math, you have a computer do it generally, it does fit in that form. You could use this a torque goal of this nature to describe other things, such as a constant torque, or also no torque, which you'd have to do for the degrees of freedom associated with a floating base. Kinematic goals can be done this way also. In this case, if we want to make joints 1 and 3 move in opposite directions, we make sure the sum of them is equal to 0. We can put a PD controller around this by concerning ourselves with the first, second, and third derivative, or excuse me, 0th, first, and second derivatives of the error. Choose quite possibly a critically dampened PD control term. And if we look at this form, it too will fit in the desired form because both Q1 double dot and Q3 double dot are affine linear functions of torques, and therefore the whole thing is. And each of those was from the inverted dynamics. So the tricky part about controlling a robot this way would be actually what objectives do you choose? Hartmut-Geyer's work is probably a great place to start. You can also use information from human studies, as well as introspection and trial and error. And you could have the goals be static if they modulate their own stiffness, or you could have it vary with contact configuration if you want. The ultimate structure is you concatenate all of the individual goals, and you solve in a least squares sense for tau, and that's your control. And eventually you can tune the parameters with a more traditional optimization in order to figure out the optimal stiffness and damping and things like that if you choose to have your controller vary with those. But the idea is that you get most of the controller set up by carefully selecting objectives. So the benefits, the control architecture is simple, basically meaning that it doesn't take a lot of ink to write. It's easy to remedy problems by modifying objectives. You can adjust weights to achieve goals like robustness and efficiency better, as well as it's numerically manageable because it reuses the forward dynamics and information from that. And it extends Geyer's work in a couple of ways, extending it to kinematic objectives, as well as arbitrary numbers of the number of motors and objectives don't need to be the same, as well as allowing it to depend on instantaneous contact forces, including rigid contact instead of just soft contact as it's currently is. Thank you.
Okay, while we take some questions, I would suggest that the poster presenters already come to the front and line up for the presentations afterwards. So, questions for Ryan?
I actually have two questions. First, do you need the acceleration feedback for your controller? And second, using this controller, how is it guaranteed that you converge to a stable periodic orbit?
For certain objective combinations, yes, it is a stable periodic orbit with a period of one step. For other combinations, it's not. It's still very much a work in progress.
Okay. And first question, do you need acceleration feedback? Because in your error function, you had acceleration.
That's, I think that's more of a feed-forward term. So if, maybe you're talking about? Next
slide.
This one?
Yeah, over there.
In the Q1 and Q3 double dot?
Yes.
Those quantities are determined by the instantaneous motor torque. So you would probably use some sort of acceleration feedback in an estimator perhaps, but you don't need to measure the acceleration to know those quantities because they're determined by the applied torques because of the structure of the equations of motion.
Okay.
I hope that answers your question. Thank you.
So we take a last question while we set up the videos.
Yeah. So that kind of depends on having an accurate model of the whole dynamics to get the equation of motion. How would it fare if you have a robot and give him a backpack or add a load or something like that?
Depending on the objectives you choose, it could either be okay or very bad. I would guess that objectives that are force-based will tend to be more robust to model mismatch than objectives that are kinematic-based, which I think is probably the agreement in this community, because computed torque can do weird things, but springs tend not to do less extreme things. So it would depend on the objectives you choose. So it's a good question. Thank you.
Okay, thank you, Ryan.
Bye.